Perth Linux Users Group, talking Linux and open source.
I'm at INET. I work on our cloud hosting platform, amongst other things. Tonight we'll be talking, as you already know, about configuration management and also automatic provisioning. What I hope you can get out of this evening's session is a broad understanding of configuration management, what it is and why it's important, a knowledge of how to use Puppet and Vagrant in some detail. Puppet's a configuration management system. Vagrant's a automatic provisioning system. And then later on, we'll talk about some applied software configuration management situations and how it's shaping the system administration field. So the agenda for tonight, we'll look at the past and present of system administration so that we can understand it in context. We'll look at automatic provisioning, then configuration management. We'll spend some time going into detail on Puppet and Vagrant. We'll then have a look at some other alternatives. We will, as I've said, look at some applied software configuration management systems, briefly consider the future of configuration management, and then hopefully we'll have some time for questions at the end, and perhaps even a little live demonstration. Right, so starting with traditional system administration, we should consider, what does a system administrator do? He has a variety of tools of the trade, commands with command line arguments, which may be in all kinds of different formats. He must remember configuration file locations, the syntaxes and the directives in them, build systems, operating system differences, and within operating systems, differences in the distributions of them. He'll learn dependencies and compatibility issues, and may require some knowledge of scripting languages. The kind of processes that a system administrator is involved in will be hardware acquisition and installation, software configuration, diagnostics, and coming up with solutions for hardware and software. And these solutions can come in the form of good architected designs, or more often than not, in some places, quick and dirty hacks. They'll be upgrading imaging-based systems for later reuse, and hopefully some amount of documenting of what's going on. So when a system administrator finds some aspect of his job mechanical and routine, traditionally a method of automating these tasks has been in the form of scripts. Automated scripts are like the theatrical scripts after which they're named, a sequence of lines to be enacted by the reader. They specify commands that would otherwise have been typed by the system administrator himself, and they're intended to achieve a desired system state. The administrator intends that the sequence of commands results in a configuration matching the target state. The states themselves are never defined in the script. The script is merely a record of steps which, under certain unspecified conditions, will produce a system of a certain unspecified state. A fastidious scripter may use conditional logic and put checks and balances into his script to be able to catch failures, but the script itself still has no notion of the state of the system that it's trying to achieve or what it's coming from. And this means that when they fail, scripts can be very difficult to recover from. They are generally not repeatable. If it's making resource allocation processes, if a script fails and is merely fixed in the middle, running it again can cause resources to be unnecessarily allocated or preemptively deallocated, and can cause problems. Manual intervention is usually required. And so bad scripts is one course of the woes of system administration. Administrators also face a problem of accumulation of hacks. In a busy mission-critical enterprise situation, If something goes wrong and there is a good solution that is slow and a quick solution that is bad, management will often be more keen to go with the quick solution to get it out the door. And even if their heart's in the right place and want to build a better solution, it often happens that something else takes priority and the hack stays there. Almost by definition, these hacks aren't documented. We document solutions and systems. Hacks are never intended to stay, and yet they often do. And it can result in a situation where no one in the company is able to understand why a system works, let alone why it's broken. Producing images of systems to quickly be able to produce new ones is often difficult. The image files are large and unwieldy, and it takes some amount of time to update them. And imaging an entire system already configured usually isn't practical, because the system will then have to be reconfigured by hand for its new circumstances, which is open to the same kind of difficulties that scripting can cause. So this is where configuration management systems come into it. And configuration management has a long history. It's only really applied to software in the last 20 to 30 years. It began as a management school of thought in the 50s, inspired by the efficiency of military departments. Corporations would have a central repository of artifacts, information about how the company is structured, which would be an authoritative source. And in the late 80s, IBM began attempting to apply this idea to computing systems. And their idea was to develop a central repository for system configuration. The system was called ClearCase. It's commercial software, and it's still available today. For the rest of this session, we'll mostly be considering free and open source software rather than the commercial variants. In many ways, the free and open source offerings have come much further than the commercial ones in the last decade or so. So about a year after IBM released ClearCase, a young physicist named Mark Burgess was in charge of his university department's IT systems, as physicists often seem to be lumped with. And he found that the sheer amount of work in maintaining the whole department's IT systems was too much for one person, and yet the university couldn't fund more. So he thought he would develop a system where he could specify what a system should look like in an abstract language and have that applied to new systems regardless of what hardware, even what operating system was installed. His system was called CF Engine, and it was free. It's evolved into Puppet, which we'll be looking at tonight. And Puppet is actually a rather powerful system today. Later on, as system requirements and demand for IT systems grew, many other software alternatives have sprung up. Some popular ones at the moment are Chef, Salt, and Ansible, amongst many others. Many corporations now see configuration management as an essential component of their system administration. So the key difference between the configuration management approach to thinking about systems and system administration and traditional scripted automation is the idea of what Puppet and many other systems call manifests. A manifest is distinct from a script in that it does not describe a series of steps devised by the administrator. It describes, in abstract terms, what the final system will look like. They're usually text-based, like configuration files, human readable. They've described state. They're usually written in a domain-specific language. Many systems, particularly the more recent ones, are using existing programming languages with special purpose frameworks for representing this kind of information. Manifests have the interesting property of being idempotent, which means that they can be run again if they break. If there's a mistake in them and they're fixed, you can just run it again. The configuration management system won't repeat the steps that it did the first time. It queries the system for its current state and works out the minimal number of steps to transition from the current state to the desired state. It makes it very easy to make small mistakes and for them not to matter, as opposed to a system administrator treading on thin ice where his mistakes have more of a consequence in time and perhaps in impact to the information that he's managing. And so a configuration management system queries and modifies the system by a use of adapters. And adapters are essentially scripts, but they have a very special purpose. They shuttle information from how the system exposes it with commands, configuration files, and other fundamental objects in system administration into the configuration management platform's internal idea of what these objects look like. There are adapters available for literally thousands of packages for most major configuration management platforms. You'd probably be hard-pressed to find a package that your organization depends on that there is no configuration management adapter available for. Since there's a financial incentive to develop these things in terms of reduced cost, the commercial backing is quite strong. So, as I mentioned, there are loads of choices for software configuration management systems. It's usually just a matter of choosing one which is best suited for your purposes. Puppet is very old and mature. It's focused towards system administrators rather than developers, unlike some of these later systems which have more of a programmer focus. And there's a reason for that. We'll go into that a little bit more later. So a complement to configuration management is automated provisioning. And that refers basically to the automation of the process of arranging hardware and getting that aspect of it set up. And the problem it's addressing is that hardware is hard. It's expensive to buy, it's time-consuming, and therefore expensive to maintain. It's inflexible. Once you have it, it's hard to get rid of if your demand drops off. It's hard to predict what your demand's going to be. It's difficult to scale. If your business is expecting a large influx of visitors to its website after a TV segment, for example, it would be impractical in many cases to buy new server hardware to have the capacity to handle this inflow with the expectation that it will be a short-term thing and your requirements will drop off again. And so this is how cloud hosting, cloud computing came about. The idea is to have your virtual machines in someone else's data center. And in these cases, you can provision new hardware at the click of a button. You'll pick an image for your system, and just like that, it's there, ready to go. Cloud hosting benefits from flexible cost models. Basically, you will only have to pay for what you use. If you're not using a server anymore, you can turn it off. If you need more capacity for a short time, you can easily get it. And the benefit here is from specialization. in that it makes sense to keep your company's business focus to the thing that you have a competitive advantage at, not to trying to manage your own installations, presumably at a lower efficiency than could be achieved by a company specializing in this. And if that's on the big end of automated provisioning, right at the other end is the idea of portable, recreatable, isolatable development environments. So when developers have to work on an enterprise system, often the company will end up having to buy server capacity for the developers to have their own environment in which they can test new code and new ideas without affecting the company's production servers. And it can be very expensive. But for a lot of development tasks, modern PCs have excess capacity compared to what the developer will actually use. And with automated provisioning systems, such as Vagrant, as we'll look at later, the developer can have his own instance of the company's resources set up on his own machine at the press of a button, and it will be identical to the production environment. That's the theory anyway. So we'll have a quick look at Vagrant before we move on to Puppet. Now, Vagrant started off with a small ambition, and it was to automate the process of producing virtual environments for developers to do their work in. And it did very well at that. We'll have a look at how it works in just a moment. The idea is that with a single configuration file, which you can ship with your application if you like, Vagrant is able to create an entire environment out of it. It's free. It comes with an adapter for VirtualBox, which is also free. So with very little cost and time, organizations are now able to recreate systems that previously would have been very expensive to simulate in the developer's own PC at no extra cost. It's quite a powerful system. Vagrant has the notion of providers. And providers give it the virtualization backend that it needs to run these systems in. Comes with support for VirtualBox, but there is commercial support available for VMware, and even for cloud deployment systems, there's an Amazon EC2 adapter. So with just a small change in one configuration file, you can deploy a system to a testing environment or to production as you need. Vagrant has a concept of boxes and instances. The box is the base instance, and there are lots of them available. There's a site, Vagrant Boxes. The dot is before the ES, and it lists configurations pre-built for most popular Linux distributions, and they can be vouched for by a community system. Most of them have build scripts, which are linked to on GitHub and other source code hosting sites. So the task of finding a base to build your system configuration upon can be greatly expedited. So how are we doing for time? So I was going to bring up Vagrant at this point, but I think we might just try and get through the slides. Getting started with Vagrant's really easy. Once you have a URL of the base box that you want to build upon, you simply need to drop into a command line anywhere, make a folder for your Vagrant instance, and type Vagrant in it, followed by the box URL, and you give it a name as well. And Vagrant will take care of downloading the image, putting it in a store for itself, and then it generates some basic configuration files for you if you need them to get started with. Once you've done that, Vagrant up launches the instance. It will do it in for VirtualBox in headless mode, so you don't see anything. After a few minutes and a bit of output, you'll be dropped back at your command line with your virtualized system running, and then you can log onto it, set it up how you like. Vagrant exposes a shared file system at /vagrant on Unix, and I'm not sure what it is on Windows. Through the shared file system, you can easily shuttle files between your host system and your virtual machine. The file system on the host side is simply the folder that you've launched your Vagrant instance from, the folder with the configuration in it. The configuration file for Vagrant is called VAGRANTEILE, and it has a fairly simple syntax. That's a lie, it's not simple at all. It's based on Ruby. It is Ruby, but you don't need to know it. The Vagrant file that you get by default has got settings for most use cases ready to go just by uncommenting them. You can do more powerful things with the scripting capabilities of Ruby if you want to. From the Vagrant file, you can set up networking. You can create a virtual network within your PC, or you can bridge onto your existing network if you need to. You can set up multiple machines. The Vagrant file doesn't specify only one box at a time. You can set up your whole corporate network from within one file, which is quite a powerful ability. There is a provisioning section in the Vagrant file, which allows you to hook onto configuration management systems. And Vagrant at the moment, I think, supports Puppet and Chef, and maybe Salt. And all you need to do is point it at your manifests directory, and it will do the work of loading up those manifests and applying them to the new system. If you change the manifest while you're using the system, Vagrant reprovision will run everything again and tell you if anything went wrong and where it went wrong so that you can fix it and continue with your work. I was going to talk about creating boxes. It's a little bit of a complicated affair. The idea is to fire up a full virtualization program, build your base system, and then there's just a few configuration aspects that you need to take care of before Vagrant will recognize it. And then you zip up the VM software's files and metadata, and it's ready to go. There's more information on the Vagrant website about that. We've seen that slide. All right, so we'll take a bit of a look at Puppet then. Puppet is a configuration management system, and it has a syntax that looks like this. It's its own language. It's designed specifically for the purpose of representing system state, and it's very good at it. It's a fairly innocuous, simple-looking thing. You might be able to tell what's going on there. In this case, a very simple manifest. We're creating a file. We name it within Puppet test file. We give it a path, a mode, and some content to put in it. And the ever-present ensure keyword there instructs Puppet on what you would like to do with this resource. So here we've got ensure present. There are other options. The opposite, ensure absent. You can ensure that the file exists but not change it with exist, and many other options that we're about to see. Again, to integrate it with Vagrant is very easy. It probably doesn't bear further explanation here. Vagrant has a directive for it in the sample Vagrant file. It's easy to get started there. So we'll go through the core types. The simplest one available is notify, and that only has one possible attribute, that I know of, and that's message. And if you want your provisioning, your configuration process to alert you when it gets to a certain stage, you can use the notify directive. Looking back a few slides, the message that notify produces is able to be specified as an attribute, or like many of the most important attributes of different resource types, it will default to the title if you don't supply one. So you don't have to have any of those attributes being set there. Just where it says test file there, if you use notify instead of file, you could put your message there and it will work. And that's a recurring theme throughout Puppet configuration. So arguably the most useful and commonly used of the core types is the file. And that's lets you have the same kind of control over files that you would as a system administrator usually, just specified in advance. So we have various options for ensuring the files there. It can be present, absent. We can ensure that it's a file, but not that it contains anything in particular, or that it's a directory, or even that it's a symbolic link. If it's a link, we give it the target attribute. If it's a file, or if we say it's present, then we can specify content or source. If you want to copy the file, with Vagrant, it's very handy to be able to copy your configuration files from your Vagrant directory, where you have them stored, straight onto the system in the provisioning step. And there's not a lot to surprise you in the file core type. An interesting one is purge, which I believe deletes the file depending on what it contains. The user type is another very common one that's the same across pretty much every system that Puppet's implemented on. You can ensure whether a user is present. You can ensure that it doesn't exist if there are any accounts that come by default with the system that you don't want to be available. And you can turn the user into a role, which is telling Puppet that this user doesn't represent a human. It might be your MySQL user or your some other service user which needs to exist, but you don't want it to be able to log on. The user can be configured in mostly intuitive ways. One gotcha is that the GID must be numeric, and it refers to the user's primary group, and the secondary groups can be listed by name or ID in the groups section. The manage home option can be used to tell Puppet whether you want that directory and potentially all subdirectories under the user's home directory to have its contents kept clean by Puppet and unnecessary things removed if not needed. If you don't specify manage home, you will have to create the home directory manually because Puppet won't create it for you. The group type is fairly simple. You can create a group and you can give it a name. The package type is interesting because this is one area that that Puppet will try and transparently make systems, package management systems, which may be very different between operating system distributions and operating systems. It has surprisingly few options, and it can be configured from the outside by the inclusion of package manager modules and adapters. But the general idea is that just by specifying the name of a package and potentially the source if the package manager doesn't provide a repository to get the package from, and Puppet will automate the installation for you. And so a lot of packages will have specific Puppet support here if their installation through the package manager is usually interactive. The service type, again, very simple. You can ensure whether a service, possibly installed by a package, is running or stopped. A lot of services ship with incomplete initialization scripts. And you might have noticed some packages won't have reload, some won't have restart. You'll have to stop it and start it again. So the service type lets you override the initialization command for all of the usual initialization directives. If the service doesn't have the status command in its initialization script, you can provide that yourself with the pattern attribute, and that just gives, that's just a regular expression to match against the running processes table to determine whether the service is running. We have the exec command, which is frequently necessary, but hopefully sparingly, where you can tell Puppet that I just want you to run this command if the results of it are not something that can be easily represented in Puppet's own semantics, especially if it's calling to an external system. In that case, we can supply it environment variables. We can give it conditions to run on, which give, we have the only if and unless directives. And we can determine whether the command has already run by giving it the creates attribute. And that's a file path. So if the command's going to leave some evidence that it's run on disk in the form of a file, we can tell Puppet that this command will create this. If that file is there, don't run it. I believe there are additional attributes to customize that behavior more. You can set up cron jobs. They work like you might expect. You can give it the same kind of timing parameters that you could in cron tab usually. You can give it a command, and that's about it. Right. So looking more generally at the Puppet language, there are a number of concepts in it which should be familiar to anyone who's done much programming. The examples of Puppet code we saw before are declarations. That's where we have a resource type followed by curly brackets, a name, and a set of attributes. That creates an instance of the type, declares it, gives it a name, and allows you to set it up. If you ever need to refer in another resource to one that's already existing, you can use reference types. And references are very simple as well. You can refer to the resource by name and by type. So if the type was file, you can say file, and then in square brackets, the name of the resource that you're trying to refer to. One strange thing is that the type name in references always starts with a capital letter. It's just how it works. Resource collectors are a powerful tool in the language. They work with what Puppet calls the spaceship operator, which is a pair of angular brackets followed by the line thing, the bar. And then you can put a condition inside it. And the condition can be any kind of valid Puppet syntax. It gives the usual kinds of comparison and matching operators. And you can use a resource collector anywhere that you can use a reference. And some opportunities to use these we'll see probably in the next slide. Just before we go on, the language has numbers. You can do arithmetic in it. It's got arrays that work like arrays in other programming languages. With square brackets, can be indexed with square brackets, and hashes, dictionaries, mapping types, which also work fairly predictably. One thing to be aware of when writing Puppet manifests is that since they're not scripts, they're not guaranteed to run in order. In fact, Puppet tends to be fairly unpredictable in the ordering it picks to apply the state that you specify in the file. So for operations which are order dependent, there are a number of ways of telling Puppet that you need it to work in this order. The simplest ones are pipelining operators. It looks like an arrow, and there are two kinds there. The simple ordering, which you can put between resources, between resource references, between references and reference collectors. It's a useful thing if you want to, for example, tell Puppet that to collect up all the resources that are packages and say, I want you to install my package manager's repository list before you do anything that's a package. The other kind of pipelining operator is done with the tilde. It's a notifying operator, and that causes Puppet to watch for changes in the resource on the left-hand side, and when there is a change, it will notify the thing that it's being pipelined to when it notices that change. Puppet doesn't run continually. It runs when you call it with the Puppet apply command, and then it stops. So the notification operator won't be able to work for files that change in the normal running of the system. It'll notice it on the next run, and then activate the step that it's been linked to. You can also order your elements with attributes, and Puppet provides us with before, after, notify, and subscribe. Before and after look like they work like the ordering arrow. It just can be a more elegant syntax if you want to put it in with an attribute that you want the following resources to come before or after a package or resource has been allocated. Notify and subscribe are the equivalents of before and after with the notifying logic. So those will cause the event to trigger if the resource is merely changed. Lastly, we have the require keyword, and that's something that you can apply at the class level. We'll see classes in a moment, but it's another way of logically grouping your resources, and require can do those kind of relations between groups. Puppet provides us with a number of ways of having multi-file projects. In fact, in large installations, it's very uncommon to have your manifest in a single file. Usually, there will be a standard operating environment, which is declared in one section of your configuration with its own files, and then individual systems may have their own configuration files stored somewhere else. So the directives we have available there are the include, and as we saw, require can glob these files together. Modules are self-contained little packages that provide both Puppet language and some scripts, and the modules are like the adapters that we've said. You can use it to control your existing systems and to interface with them, and provide common functionality out to the rest of the language. The idea of having multiple hosts under control is referred to as node configuration in Puppet. Node is another keyword like class that you can follow with curly brackets, and the configuration within will only be applied to that node. You can configure your hosts to take on any node name you like. It's best practice that you do use the host name of the system and not some wacky other name to refer to your nodes, lest you get confused and it becomes hard to keep track of which systems have which configurations applied to them. There are heaps of adapters that I mentioned. it would be silly to try and enumerate them all, but some very popular ones are apt and yum, which provide additional custom functionality above Puppet's native package implementation. Web servers and databases, it's all there. Pretty easy to figure out. Puppet is available on Windows. There's a Puppet agent that can apply manifests to it. Not all of the core types are supported. For example, Windows has no simple notion of packages. There is some partial support which is able to install a package for you but not detect if it's already been installed, which can cause problems. I hear that that's getting better recently. So best practices, as I was mentioning, use modules where possible. If you have some sort of custom system at your organization, rather than putting the configuration for that system in with a host-specific configuration, move it out into a module, bundle it with its scripts, and then you can move it to different hardware. And then with a simple require keyword, you can bring it into other systems. Use version control, of course. We'll come to some consequences of that later. That nodes should match host names. And the file hierarchy for storing manifests is a hotly debated topic as to what's the best. But a common one is to put your main system manifests, your individual machines in a node, in a manifests folder, to put your modules in a modules folder. If you need to set up any users, since this is a thing that can commonly be the same across many systems, it helps to have a users folder for you to have those configurations in, and services for any other infrastructure requirements. For example, if you needed to set up your authentication to your company's LDAP server or use of the mail server, the services directory is where that kind of stuff is normally put. And the last thing is to use classes to separate your users depending on what relationship they have with the organization. So you put your system users in a class. You'll put your administrators and staff in one place, and customers who might access the system, and general public users in another section to themselves. And that means that you can't accidentally, with a resource collecting operator, pull in users from both the service user privilege level and the untrusted public privilege level, and apply the same rules to them. How are we doing for time? 8. Right. So we'll quickly look at some alternative options to using Puppet and Chef. I think we've covered in these last couple of sections most of what you would need to know to actually operate a production configuration management system with Puppet and Vagrant. There's quite a large installation at INET that's being worked on. It doesn't quite cover all of our systems yet, but it's getting there. And we don't stray very far from the directives and syntax seen in the last slide. But there are other options, some of them becoming very popular. And two of the most popular ones, at least in the free and open source space, are Chef and Salt. Chef's been around for a few years now, I think at least half a decade. It uses Ruby as its language. It's more procedural than Puppet. It's still not a matter of listing commands to execute on a command line, but Chef has the notion of recipes, which specify instructions in high-level terms for how to configure parts of the system. So there will be a recipe for setting a system up as an Apache web server, as a reverse proxy, whatever you like. Chef, since it's based on procedures and not trying to represent your entire system state at once, is quite well suited to partial integrations. If you can't get buy-in from whoever you need to, you can start to include chef recipes into your deployment process without having the overhead of a system which wants to log in periodically to check how things are going. I say want to, but Puppet does nothing of the sort. You have to instruct it to check manually, but there are some good reasons to do so. Chef uses SSH to manage its nodes, so it will log on to the server and then run its own commands on files that it's copied over to execute them and set up other machines. Chef's other notable thing is that the order that you specify things in the files is the order in which they will execute, unlike Puppet. Salt is newer still than Chef. It's designed to be massively scalable. It's built on 0MQ, which, if you're familiar with that one, you'll know it's very fast. It eschews normal data transport protocols and re-implements its own at the same level as TCP. Salt configuration is done in YAML, so it's very simple to read. It's designed for time-sensitive operations. Salt is able to be told that it needs to deploy a particular configuration to 5,000 machines within a 5-second window and be able to tell you which ones didn't make it in time, which can be important for sensitive mission-critical deployments. And because of this reliance on 0MQ being installed, which requires a little bit of network setup, it's more complex, but it's still becoming very popular. It has many more contributors than Puppet at this stage, and it seems to be a more and more viable option, especially for companies where time is a relevant issue. The other software configuration management platform I thought we might consider was Ansible. This is the new guy on the scene, and the draw card to Ansible is that you don't need to install any software on the target machines that you want to manage. It can log into them, do its thing, and get out of there over SSH, requiring very little setup. It's good in situations where you're not using automatic provisioning. For example, if you have already invested in a server farm and you have a lot of hardware resources, and Ansible is able to go and configure them for you without a lot of investment in setting the individual machines up to be ready for it. Ansible uses Python as its state language, which is nice. I think we might take a break here. After the break, we can consider some applied software configuration management approaches, and some of them are quite novel. I think they're interesting. But we'll have a look at it after dinner. Oops. Okay, so we're going to look at some applications of software configuration management in terms of what having your entire system state stored in configuration like this can enable you to do that wouldn't perhaps be practical with traditional system administration techniques. So the first and most obvious one is that you can put all of your configuration in a central repository. And that's great for compliance auditability. You can tell everything about your network from looking at a single source. In theory, system administrators may still be able to log onto the systems and apply hacks, but the approved system configuration is stored in a known place, and that's suited to large installations and particularly enterprises that aren't doing software development themselves. In that case, they might prefer the approach of storing the configurations required to run the packages they're developing with the packages themselves. This is what we're doing at IONET. It makes some sense if the developer has created a certain environment of their own that the software is known to work in, and they need to be able to deploy into a compatible environment that, rather than the traditional approach of relying on the package manager to be able to find the correct dependencies, which works well for packages, but is inflexible to other environmental requirements. Specifying the required state for the software to be able to run with the software enables the developer to cut out a step of documentation, of communication, and of course of manual setup of the system. It can be particularly problematic in a large organization when the people who are developing the software have limited contact with the people managing the servers that it ends up running on. To be able to remove some worry from that step can be a big bonus. Another potential thing you can do with your configuration under management is running kind of controlled burns on your network. And if I was to come up with a name for a software program that deliberately kills your servers, the term that comes to mind could be virus infection or malware. Netflix call it the Chaos Monkey. They've released it as free software. You can download it from GitHub, and they run it on their own networks. And basically, it does what's written on the box. At regular intervals, it will terminate one of their servers just completely offline. And they're able to do this because under configuration management, setting up a new server is not a massive task that requires human involvement. In fact, the monitoring system that notices that the failover system is activated can rebuild and reprovision a new system to replace the primary one without any interaction. And the benefit of doing this is that you can build much more resilient systems and networks than you could if you were merely hardening them in theory, in the hopes that when an attacker strikes, they won't be able to do damage to your system. They choose to do the damage on their own terms, so that when it happens to them and they're not expecting it, that the damage that can be caused by it is limited. It's called a fail-fast approach. If something's going to break, we want it to break now, not when it's going to really matter when we're under attack. And the other benefit of running controlled burns is that if some rogue administrators have been a bit lazy and they're not updating the configuration files, and they've installed hacks on the machine to work around problems, when the Chaos Monkey strikes and that machine's gone, once it gets replaced with a freshly configured machine, it won't work anymore. The hacks will be washed away, and either the administrator has to keep applying them, or he can do the right thing and update the configuration management. Another idea which has gained some steam, as far as I know, there are no large corporations doing this yet is the idea of immutable deployments. And immutability, the idea that the state of an object can't be changed, has become fashionable in programming circles in the last few years, especially with the advent of functional programming languages, Haskell and F#, rising in popularity, especially since Microsoft started shipping F# with Visual Studio. And the nice thing about engineering a system where the components can't change is that you can reason logically about what the state of the system is going to be after a much longer series of events than a dynamic system where memory and configuration and state can change. To work out what's happening on a server that is mutable, where it's dynamic and settings can change on it, you'll have to log on to that server and observe the current state in order to work out what's going on. In an immutable deployment, you might not even ship your server with SSH. The administrators can't log on to it and change anything. And so you know, as long as it hasn't been compromised, separate question, that your system is exactly as it is specified in your configuration management repository. And this might seem like a subtle difference between simply not logging on and putting in hacks. But the situation is not that uncommon where it's not so simple a choice. If something breaks, there can be pressure from non-administrators and even from within the administration team to just get it fixed as quickly as possible. And this kind of quick fix can be at the expense of the overall resiliency of the system. It would be easier to tell a manager, no, I can't actually log onto this server and install a quick fix, than it is to tell them, yes, I could log on, but our policy says that we're to go through the configuration management system instead. Central management is a kind of nifty consequence of a central repository of configurations. We can now have one web application which has control of all the systems in the network and is able to update their configurations from a single place rather than having to rely on individual permissions or group permissions to each of the servers for all of the people who need to be able to get onto it. The Puppet provides Puppet Enterprise, which does this kind of thing. That's a commercial solution. VMware has its own solution for this with other more modern package management systems like Chef and Ansible and Salt, as we've seen. These have management of multiple nodes built into them. They're designed to talk over SSH or some other messaging protocol to do this, and so this kind of functionality comes very easily for them. One of the big benefits of having a system that you can reproduce instantly is that you can do automated testing on new configurations. This is something that software developers have been doing for a long time now, where when we compile a new package, or rather when we are ready to commit source code to the main repository, the source code hits the repository, and then before it's allowed to make it into the mainline stream, the build system runs on it. It checks if it compiles, it runs various tests on it to make sure that nothing is broken. You might miss a test, in which case you might miss a particular error, and then you can write a test for it, put it into your automated testing system, and be reasonably sure that you're not going to let that same mistake happen twice. And configuration management extends this kind of powerful defensive model against deploying bad systems to system administration, rather than system administrators being able to go and put their own changes on a machine. If they have to change it in a configuration file and then push that to a repository where the change can be built into a virtual environment, tested for all kinds of common errors, and then and only then will it move on to the next stage and perhaps be incorporated into the main repository and pushed out to the machines. We're able to avoid a lot of system configuration related issues that could arise without such a testing environment. And the software development concept here is called continuous integration. We want to be able to get code and get changes live without there having to be extensive manual testing to make sure that these kind of problems don't take place. Often system administration, firefighting is time sensitive, and having to test a new system that you've built yourself before deploying it can be a huge cost. This enables the organization to have some sense of sureness that a change is not going to break anything in the system that's been broken before by previous changes before it reaches deployment. Change management, similar to what we were just saying, the idea is that changes can not just be tested, but they can be reviewed. And it's a feature, again, of many common source code repository systems. The Atlassian Stash is a popular one, GitHub is a popular one. The notion of a pull request, and the pull request, which pulls one developer's contributions into another branch, can be attached to review tasks and required that someone more senior at least has a look at it before it gets incorporated. So with the review and test automatic testing model, we can end up with quite a responsible approach to getting changes out that ensures that those changes are accountable, not just to the person making them, but to someone perhaps more skilled who's seen the change first. With the testing, we end up with quite a robust deployment model. Development environments, we've already talked about this. The configuration management can recreate big systems, no problem. We're running out of time, I won't harp on about this. So looking at the future, very briefly, a lot of the future to come is just going to be in the form of corporations taking a more active stance towards configuration management. It's been kind of a ground-up movement in that it's been driven by frustrated developers and sysadmins rather than necessarily the upper levels of management. And as the benefits are starting to show, the companies that embrace it are doing very well, being able to manage huge web deployments. Google are very good at it. Yahoo are very good at it. Amazon are very good at it. The case becomes more compelling, and we'll start to see more widespread adoption. And in a previous edition of this talk, I described it as the death of system administration. It's perhaps a bit dramatic, but as this stuff becomes more planned and more code-based, a lot of these kind of tasks are ending up being done by developers, or as the new term for it is DevOps, developer operators. And that's a popular and gaining popularity field in software development. We'll see more integration with software development lifecycle approaches. We'll see integration with agile development tools. There's an Australian company, Atlassian, who do a very good stack of software development and not so much system management, but a good set of IT and development applications. And Atlassian, I think, are looking at integrating some form of configuration management into their automated testing platform, Bamboo, which is another useful package there. Configuration management fits in very well with the lean management methodology, where there's a focus on getting tight feedback loops. If you screw up, you want to know straight away, because as humans, we're better able to learn from things when we get the consequence of our actions closer to the time we make that action, not later. Another lean idea, which is supported by having configuration management systems, is the idea of validated learning. If a company wants to be able to test some hypothesis about customer behavior or customer values, it's nice to be able to run 2 simultaneous instances of their software and be able to measure the results and take them down and integrate that learning from what they observe into their next cycle very quickly. That's something that being able to rapidly spin up machines to perform an experiment and turn them off again is helped by. And that's it. Thanks for listening, guys. I hope it was of some interest to some of you. If you have any questions, I'd be happy to field them. And I don't think we'll have time for a demonstration tonight, unfortunately, but it's very easy to get started yourself. The Puppet and Vagrant software is available for free download. Enjoy.